We are live now. You can start.
Okay. All right. Good morning, good afternoon, good evening to you all. I'm Engineer Mikailu, a student of Transportation Engineering in Bayero University, Kano. So before we start the workshop, which is hash functions, I would like to briefly introduce DoraHacks. So here's what DoraHacks is all about. What is DoraHacks? That's the first question. So DoraHacks is an open source knowledge community focused on cutting edge technologies such as encryption and Web3, co-built by hackers. So DoraHacks regularly organizes knowledge sharing sections in the form of live broadcasts, audio, and text. The topics covered include L1 and L2 consensus algorithms, architecture, and related content in GitHub repositories. Some of the specific topics covered include scroll, that's or polygon ZKEVM. We have the agents hybrid proof system. We have the stackware. We have Aztec, optimism, Zecre, Aptos, Move, cryptography, that's including zero knowledge proofs, that's ZKPs. Then public key encryption, hash functions, and lattice ciphers. Then we have distributed systems, the Ethereum protocol stack, quantum computing and quantum information, and satellite communications and spacecraft system designs. So basically that they cover all these things I mentioned. Then we have to go through the overview of DoraHacks where all these things are being captured and they're all hosted on. So DoraHacks. Currently, DoraHacks platform offers various types of bounties such as this. So the bounties they offer are translation, writing, technical research, development, bugs, and more. So at present, the PGS program is available for Evmos and Akwe. So anyone interested can just join. Firstly, here is their website, https. You should make sure this is how it looks. dorahacks.io/DAO bounty. So let's take a quick peek at how it looks. Okay, beautiful. This is how DoraHacks DAO bounty site looks. So you can see there are ongoing bounties already. Like this first one, you can see the taproot, you can see the Cosmos, MEV, you can see the Hacker DAO, Hacker Dōjō, you can see the beginner and the experts. You have everything here. Then we have the Z Cave, we have the Evmos. The last one I did was Evmos. Yeah. Then we have the NSATs, Aptos, Ton, yes, and so many more. So you just check for interested hackers. Just check around, find the one that best fits you. If you are into NFTs, we have one. We have projects for NFTs. They are fine tuned for you. You could go and check and participate um in the hacker bounties. I think I'll click on one quickly before we start our presentation. Um, okay, let's say distributed key generation. So you can see the participations is 8 days. So you can participate if you are not a member of or if you are not on this Dora hacks. You could go to this website and register. You see my profile here. So you just go in and sign in and register. Okay. All right. So we'll start our presentation now, which is all right. here's the outline for our presentation, which is on hash functions. So we'll be talking about the introduction to hashing, principles of SHA-1 and SHA-2 hash algorithms. We'll be talking about the similarities, then the differences, and finally the ZK-friendly hash functions. Alright, so we'll be starting with the introduction. What is hashing? So hashing, the digital space was or is or will never be safe as long as countless cyber criminals and hackers are lurking around and looking for ways to lure netizens and steal their digital their data. So fortunately, users have started being on their tools and become alert of their digital footprints that's taking care of their um, data security. So thus, everyone using the internet must cautiously and consistently validate legitimacy of each attribute. So how, when you ask? That is where hashing comes in play. So hashing defines a mathematical algorithm that employs cryptographic techniques to transform plain text into. Let's quickly take an example. Like, suppose your name is Ella and you must enter into a website while keeping it confidential. Applying the hashing algorithm will transform your name or yeah, to transform your name into like a kind of like a decrypt text. Here is an example here. You can see so Ella will be converted to these 28E, all these random numbers you can see here. Now similarly, okay, oftentimes people mistake hashing for encryption. They are not the same things. However, encryption actually is actually a two-way function, while hashing is just a one-way. The key difference between them is that encryption can be reversed, while hashing can't. So here's another example. So from this figure, you can see your input message plus the SHA-1 hash function. It gives you a hash value. Another example can be seen below. We have Fox. When you put it to a hash function, you can see like this digest is like the output given. You can see DF, CD, and all these numbers there is the hash for Fox. While tired Fox jumps over the blue dog. You can see the hash functions. Uh, You can see the hash functions are kind of the hash functions are kind of different once you change a particular letter. So no two hash are actually the same. When you change a particular letter, it gives you a different hash output entirely, right? All right. So we go to the applications. We go to the applications of hashing. So what is the applications of hashing now? Here's what we're going to explain. So in the banking sector makes practical use of this hashing in one of its applications. Let's say you have applied for a credit card and you enter the password to access your account. Though you are using a bank server, it does not serve your credentials in the system. Rather, it will run your password via the hashing function and save the hash as your password. That way, it even makes everything like more secured. So, what's hashing for? One, you could say for verifying the integrity of data. Two, for authentication purposes. Then also for storing confidential information, just like in the case of the banks. So, what is the SHA now? The SHA is the secured hash algorithm. That's what the acronym stands for. It's a cryptographic algorithm used for hashing data and certificates. In SHA, each piece of information or data has a unique hash that does not match any other data, as we stated earlier. So making duplicates is practically impossible because it doesn't work that way. So furthermore, hash depends on a generated out hash from data. The final digital signature is also distinct. Alright, so we have the SHA-1 and we have the SHA-2, which are the two things we are going to like talk about right now. So the SHA-1 is a cryptographic hash function that uses 160 bit output represented by a 40 digits long hexadecimal number. The algorithm builds upon principles similar to those used in the design of MD4 and MD5 hashing algorithms, so which found application in the early 1990s. It generates a unique message of length that's less than 264 in blocks of 512 bits. So simply put, computing a message digest, the algorithm processes a block of about 512 bits in sequence. That's how it works. So distributed revision control systems such as the mercurial, the monotone, and the git also utilizes this hash. They also use it. Okay, so let me briefly talk about the SHA-2. So the US designed the SHA-2 as a cryptographic hash function. So National Security Agency, while it works the same as the SHA-1, it offers a higher security level made to eliminate the shortcomings of the SHA-1 algorithm. That's why this was created. So it is a family of four hash functions, and here are their names. The SHA-1, the SHA-224, the 256, the 384, and the 512. So those are the four families of the SHA-2. So the SHA-256 works on 32 bits, while the 512 works on 64 bits words, which is why both use different algorithms. However, organizations widely employ them to authenticate and sign digital signature certificates like the SSL, code signing certificates, and also documents. I think we've laid that to rest. Okay, so we'll go to the principles. What are the principles of SHA-1 and 2? So the SHA-1 are both based on the the Demgard construction, which iteratively applies a compression function to a message to produce a digest, right? So the compression function is a cryptographic function actually that takes a fixed size block of data as input and produces a fixed size block of data as output. We'll learn more as we go further. So here is the application. What is the application of the SHA-1 and the SHA-2? So here is the digital signature. A digital signature is a cryptographic technique that allows someone to verify the authenticity of a digital message or document. So the SHA-1 and 2 are used in digital signatures to create unique hash for a message or a document, and they are not tampered with in that manner. The second one is used for message authentication codes, as the MACs. So it's a cryptographic technique that allows someone to verify the authenticity of a digital message. That's like both the SHA-1 and 2. They are used in MACs to create unique hash of message. So the hash can be used to verify that message that has not been tampered with, and that it has been sent by the authorized sender. So you can use to check that the sender can just like, okay, I want to confirm this was actually sent by me. So the hash would have to match with the one sent since it can't be altered. So now the last one is secure hashing and authentication algorithms. So SHA algorithms are a set of cryptographic algorithms that can be used to create a secure hash of message or documents. Alright, so I think that should be about it. Then the last one, security of the SHA-1 and 2. So as we stated earlier, we said, okay, the SHA-1 was once considered to be a secure hash algorithm, but from all what we've read, the second one was created after they've seen the vulnerabilities of the first one. So yeah, the SHA-2 is the more preferred one if we are to advise which one to go with. So what are their similarities? Okay, the first one is both they are both cryptographic hash functions that are used to create a unique digital footprint of a message or a document. So this fingerprint is known as a hash or a digest. Hash functions are used in a wide variety of applications, including digital signatures, message authentication, that's the MACs which we discussed, secure hashing and authentication algorithms, the SHA. Another similarity is they are both based on the Merkle-Demgard construct, which iteratively applies a compression function to a message to produce a digest. That's just what it does. And the main difference will be discussed. Okay, so these are the other similarities. Both algorithms are relatively fast and efficient to compute, and both algorithms are considered to be secure, although the SHA-2 is considered to be more secure than the SHA-1, which we discussed earlier as well. Okay, so I think we will go to the differences. That is our next. Okay, so what is the differences between the SHA-1 and 2? So one of the differences is they are both cryptographic hash functions that are used to create a unique digital footprint of a message or a document. Now, this fingerprint is known as a hash or a digest. Hash functions are used in a wide variety of applications, which is including um, message authentications and authentication algorithms. Okay, sorry. Okay, sorry. Here are some of the differences. The SHA-1 is generally faster than the SHA-2. However, the difference in speed is relatively small and is not a significant factor for most applications. That's speed. The second difference is security. The SHA-2 is considered to be more secured than the SHA-1. This means that it is possible to find two different messages with the same SHA-1 digest. So it's not really that much secured compared to the SHA-2. This vulnerability has led to the development of newer and more secure hash, which is the such as the SHA-2. The last one is compatibility. So the SHA-1 is more widely supported by software and hardware platforms than the SHA-2. However, the SHA-2 support is becoming increasingly common. Most people now they are adopting the SHA-2, they are leaving the SHA-1. So which algorithm do they use? So if you are developing a new application, it is recommended to use the SHA-2, as I stated earlier, instead of the SHA-1. So the SHA-2 is more secured and is becoming increasingly common. So if you are supporting an existing application that uses SHA-1, it is important to weigh the risk and benefits. So you look at the risk and benefits and if you should change to or migrate to the SHA-2. It's highly advised. So this brings us to the last point, which is ZK friendly hash function. So this ZK, that's zero knowledge friendly hash functions. So these zero friendly hash functions are a type of hash functions that is specifically designed to be used in zero knowledge proofs, that's ZKPs. So these ZKPs are cryptography protocols that allow one party to prove another party that they know a secret piece of information without revealing the secret itself. So kind of like two secrets are being shared, but not literally being shared through something. So these ZK-friendly hash functions must have certain properties in order to be used in the ZKP. So these properties include, these are the most important properties that they just need to be included. So the first one is the pre-image resistance. It should be difficult to find a pre-image for a given hash. So this means it should be difficult to find a message that produces a given hash value. So the second one is collision resistance. So it should be difficult to find two different messages that produce the same hash value. Yes. The next one is the efficiency. So the hash function should be efficient to compute both in terms of time and space. Then the last one is the ZK friendliness. It must be ZK friendly. So the hash function should be compatible with the ZK piece. Yes. And this means that it should be possible to prove that a message has been hashed using the hash function without revealing the message itself. That's just the concept of the whole stuff. So I think we'll move further to the usage. So the usage of the hashes in the ZK protocol. So a hash function is useful in the ZK protocol. So one famous example is the membership check in the Merkle tree. So if we check it and for a Merkle root, that's the R, the prover will claim knowledge of the witness. That's like W1 down to WN. The N is just number. It could be 1,000 number, such as yeah. So the formula is down there. It's based on this formula that is down there. H into bracket H, another bracket H, then another bracket again. W1 2 close bracket W3 down to WN. The series keeps going till you get to the number. The number is infinite. So to prove their knowledge of elements W1, sorry, which is a member of the Merkle tree, we do integrate checks like using the vanilla hash computation to retrieve the pseudo-random strings. So from the fixed length, the length it and signing of the transactions. So this is a big question. Why are ZK friendly hash functions required? Why are they even required? Okay, let's quickly dive into that. So the standardized hash functions such as the SHA-2 and the SHA-3 are extensively studied and their security is widely believed. But moreover, traditional softwares and hardware implementations of them are efficient compared to the competitors. Yeah. So when we need to evaluate the hash in ZK protocols, it seems nice to use the SHA-2 or the 3. However, many ZK protocols are using relatively unfamiliar hash functions such as the MIMC, the Poseidon, the Rescue. I think Rescue and FIntion, and instead of the SHA-2 and the 3. So for now, most of the ZK protocols prefer the MIMC, Poseidon, and Rescue or the FIntion. So the main reason for this is that the efficiency in ZK protocols is determined in quite different ways from traditional metrics such as running time, power consumption, and gate count. The efficiency of the circuits in ZK protocols depend on the algebraic structure. So generally, if the circuit is represented as simple expressions in a large field, it allows efficient proof in terms of like prover execution time and proof size. But unfortunately, traditional hash functions are inappropriate for this. So they just would like to go with these ones I listed above MIMC, Poseidon, and the rest because it gets the job done. It does what is needed by them. So we'll briefly look at the examples. Some of the examples are the MIMC, the Poseidon, and the rescue or vision. So we'll first take the MIMC. So the MIMC is the first ZK friendly hash function introduced in Asia Crypt in 2016. So although more efficient ZK friendly hash are suggested after the MIMC since it was the first one, it's still widely used even today. So the design of the MIMC is extremely simple. see the function is the fx function equals to x raised to the power of the 3 and is iterated with sub-key addition. So this concept is already proposed by the Neighbor and Knudsen in 1990s called the KN cipher. Then under this MIMC, we have the MIMCNN, n/n. So we first take a look at the block cipher. So now this is under the block cipher for the MIMC. The block cipher is constructed by iterating R rounds, where each round function is described as fi, that's function of x, equals to x plus k plus c. This is more of like a constant, then raised to the power of 3. So in the round function, the c1 is a round constant, yes, and k is the key in the equation. Sorry, yeah. So the field is the f subscript q, where q is the large prime, or q equals to 2 raised to the power of n to any number. Then the encryption process is defined as this formula written down here. So from the formula, and also we take note for the c subscript 0 is fixed to 0 because CO does not affect the security in any way. So for the field FQ, we have the FQ function of x to x raised to the power 3 has an inverse if and only if the GCD 3, that's q minus 1, is equal to 1. This is like kind of a condition. Is a condition. So therefore, the author suggested choosing odd n for q equals to 2 raised to the power of n and q equals to 3k plus 2 for prime q. So now for the round constant C1, it's recommended to be chosen randomly for the first and hand-coded into implementation to show nothing of my sleeve on the round constant. So here, the formulas are denoted for the down places. Also, here is a representation of how the whole circuit looks, coupled with the equations that were first placed up there. And the next one is the MIMC2n/n. It works a little differently. It's also it also it is also possible to construct a block cipher with same nonlinear permutations in a phase-star network. So the round function is MIMC2n/n, described in the below figure, and can be defined as XL, XR, and here the equation over here. And here's how the structure looks. So the round function images. For further studies, maybe I'll provide the links for you for those interested to know further. So hash functions now. The hash functions for the MIMC. This is structure, this is how it looks. It makes use of the sponge construction. So you can see the P1 over here is input, while the Z1 is hashed output. Here is an output over here. And the unused capacity C should be twice the desired collision of pre-image attacks. So the security analysis, yeah. So you can see the security analysis. It has a few, it's based on GCD attack though, but it has a few equations that it's based on, like the EK, D1, plain text ciphers, and pairs. Sorry. And we have the R log base 3 and Q, degree D. So it's based on all these. And of course, the D is equals to 3 raised to the power of R, where R is D. So it's not complexity. Since the single constraint can square the value, there are two R1CS constraints in each round, which is x2, which is equal to x times x, while the x3 is x2 times x. To generate the 256 bits output hash for the 256 bits input x, while the sponge construction is used in the details. Okay, so now the stack complexity works similarly, but no, works differently actually, because it uses a constraint polynomial which is based on the equation down here, and this down here. So D is also 3. Then the efficiency metric is T multiplied by W multiplied by D, where the W is 2, that's the number of columns, while our T is the number of rows. We have 324, and the maximal degree is 3. So you multiply all, you have 1944. And the implementation is also in here as well. Okay, then we'll move to the next, which is Poseidon. So this Poseidon is yet another ZK-friendly hash function suggested by Usenix in 2021. It's a more recent one and also widely used. It's based on Hades design strategy. So let's look at this Hades design strategy. So SPN is a famous block cipher algorithm. For example, the AES uses the SPN structure by applying enough alternating rounds for substitution boxes and permutation boxes. The attacker is unable to recover a key from plain text and cipher pairs, right? So Poseidon hash function now. I think the structures are just there, the most important aspect of it. So you can see the arc, the M, you can see the different locations of the S for the RF round, the RP round, and the RF round, like more of like an input, the middle, and we have the output. Just the same with the first one. So it's based on RF equals to 2 RF. The number of full S boxes is the number of the partial S boxes images. That's from the Poseidon paper. You could also, I think I also drop the link for that as well, for those who want to learn further. And then the equation goes down. It uses the MDX matrix, which is this, the MIJ, 1 all over XIYJ. So it's based on this metric formula, the country metric. That's for the linear layer, which is defined by this. Right? Okay. So the snack complexity, you can see the snack complexity is more than that of the MIMC. The X2, because the X times this, it has the X4 and X5, whereas that one wasn't up to this. Then the stack complexity, similarly, but you can see the value, we have 425. So we have the RF plus the RP, which is equal to TWD. So you can notice the slight differences. Okay, then finally, we are looking at the rescue or division. So there are also ZK-friendly hash functions following marvelous design strategies. They are suggested in the FSE 2020. So the marvelous design strategy is based on a substitution permutation network parameterized by a tuple as QM, pi, M, V, and S. So here's what they are. The Q is the field. The Q is the field F subscript Q with Q, either with the power of 20 or a prime number. Then M, we have the state, which is M, the element of Fp. Then our pi, we have the pi subscript 0 and the subscript 1 in the S boxes. Then we have the M, which is the based on the MDX matrix. Then we have the V, which is the first step constant, and S, the desired security level. Right? So basically, that's how the so for the pi zero is obtained directly from pi one ratio pi zero, which is equal to our pi one is an inverse of our pi one. So our pi zero equals to inverse of the pi one. That's the linear layer is chosen by the Vandermonde matrix, and that's just little information on it. Then the vision, sorry, the above was on rescue, while this one is for the vision. So to be precise, the S box this you select for the vision, the S box you select like degree 4, which is denoted by B to be more precise. Then they don't have the x raised to power 3 in terms of the B formula. So we have the dx equals to b subscript 4 x raised to power 4, right? Then you can't see the x raised to power 3 because it's not there. It's not there for a reason. So we have the b2 x raised to power 2, the b1 x raised to power 1 plus the b0, of course, 0 to power 0. The x raised to power 0 is just 1, so no need of writing it here. So the b is linearized on F2 and it gives benefits for other computation settings such as MPC, right? So, however, it is irrelevant with snack and stack. So I don't think we even need to, yeah, settings. So we don't need to discuss it any further. After B is chosen, pi 0 and pi 1 is pi 0 x, and we have the B inverse x inverse, while the pi 1 subscript 1 x is B in brackets x inverse. So finally, the number of rounds is doubled and the longest reach attack, which means 100% safety margin is added, and round number varies from 10 to 16. This is a more preferred version. Most people use this rescue. Here's the structure for the rescue. Rescue works differently, but I just added the two because they are often seen as same, but they are not. But the vision is highly secured, highly secured. So they are based on. Uh, so this is the rescue. That's why the rescue has the stack and the snack complexity, but the vision is what we are basing on. So, all right. So the conclusion: the algebraic simplicity of AOCs often allow attackers to attack ciphers. Therefore, it is recommended to use ciphers that have been published and proven, like the above ones listed. So also, it's important to note that we didn't list all. I didn't mention all. Like the GMIMC is also there, the Jarvis and Friday, but all of them, their design rationale follows suit with these principles that have been covered here. So here's the summary. We have the AOC, the R1CS for the snack, and the AET for the stack. So you can see the rescue is highly computational. Like it's very, very excellent. The figures are very nice. Also, same with the vision, I think. Yeah. Zero knowledge proof. Okay. All right. So here are some few functions that are used for of the application. So we have the zero knowledge proof, the secure computation, privacy preservation applications. These are some of the ZK-friendly hash uses that we have. Okay, let's quickly look at them. So for the zero knowledge proof, we have the ZK-friendly hash functions are used to construct zero knowledge proof. For example, ZK-friendly hash functions are used for ZK snacks and ZK stacks, which are the two ZKPs that are used in a variety of blockchain applications right now. While we have for the secure computation, we have the ZK-friendly hash functions, which can be used to construct secure computation protocols. Secure computation protocols allow multiple parties to jointly compute a function over their private inputs, like without revealing their inputs to each other. Also, one of the bases of why these ZKs prefer using these MIMs, the Poseidon, and the rescue and eviction, because they provide all these things. So the last one is privacy and preserving applications. So ZK-friendly hash functions can be used to develop privacy preserving applications. So for example, ZK hash functions can be used to develop privacy preserving payment systems and privacy preserving voting systems, right? So these things are highly secured. And here are some of the references I wrote. And sorry, permit me, these are the acronyms I used. I think I used AOC just now and I didn't spell it out. So AOC means arithmetic oriented cipher, while AET is algebraic and execution trees, while R1CS is rank 1 constraint systems, while ZK snacks is just an acronym that stands for zero knowledge proof succinct non-interactive argument knowledge, while the stack is uh, scalable transparent argument knowledge. So I think with this brings us to the end. Thank you for listening. I hope it was well explained to you all. Yeah, thank you. So at this point, I think I'll ask for questions. If there are any questions, please. Is there any questions? Any comments?
Hello, can you hear me?
Yes, I can hear you.
I see the YouTube and there are no questions.
Okay. Okay.
Thank you for your presentation.
Yeah, thank you for your time. I appreciate the
See you next
opportunity
time.
to. All right.
Goodbye.
Thank you. All right. Bye.